All right, so today we'll be talking about multiple regression. So basically an extension of what we did last week with simple linear regression, but just now we're leveling up to multiple regression. So when we were doing simple linear regression, we had just plotting one variable to predict one other variable. In multiple regression, we're using multiple independent variables to predict one independent variable. And we'll take a look and see all the other different things to consider when we're doing multiple regression. So as you can see here, I have a couple sections, just overall like how to do a multiple regression. I'll be talking about categorical variables a little bit, multicollinearity, feature transforming, as well as I'll dive back into model validation and also using the other library, Scikit-Learn. So those are all the things we'll be talking about today. It's going to be a little bit of an information overload, but this notebook is here for you. Pretty much each section corresponds to a bunch of lessons in topic 19 as well. So hopefully that structure will make it easier to get through. All right, so just to start, let's use this information, which I should import pandas real quick. Let's see, as pd. There we go. So we're going to use this data set, which is the miles per gallon car data set, where we're trying to predict miles per gallon. Just as a baseline, or just to show the syntax of doing a multiple regression in stats models, we're just going to throw a bunch of these variables into our regression. So as you can see, the code is very, very similar. In terms of the formula that we were using, previously you had something that just looked like this, you know, dependent variable, squiggly line, independent variable. But now with multiple independent variables, all we have to do is string them together with plus signs. And what's really great is that stats models can automatically parse this string and figure out which are the independent variables to look out for. And again, these independent variables refer to the column names in the data frame. One thing really quickly to mention regarding this formula as a kind of a tangent is that, remember I mentioned that this formula is actually the syntax of R, the syntax of the language R. So while you're working on your project, or if you're doing multiple regression, just watch out, because certain symbols can lead to problems with parsing the formula. I think in the recent project that my other cohort did, they found that if you had like periods in any of your column names, like a dot for like decimals, if you have dots in your column name, it actually throws it off. So when you're doing your data cleaning, consider that as well. And also if you get an error in your formula or in your model line, I think this is where it'll give you an error if you have a symbol that doesn't make sense. Definitely check for that. I believe percent signs also don't work. Dollar signs might not work as well. But that's because these symbols mean something else in our syntax. So something to look out for. But other than that, the syntax is the same. When we're fitting the model, we're using our OLS, feeding in the formula, feeding in the data frame, calling .fit to fit the model, and then same as before, we can do our model summary. Where are all my imports? Did I lose all of my imports? Let's see if I remember this. Import stats models .api as sm. Does anyone know if that's the right one? Let me quickly pull this up. OLS. Oh, nice. As sm. There we go. Hopefully this will be the last thing that I forget to. There we go. Why is this not working? sm.ols. Sorry guys, I don't know what's happening here. Did I spell stats models wrong? How's that PPI? If anyone sees my error, please let me know.
You might need statsmodels.formula.api.
.formula? All right, let's see. Like formula? Let me see real quick. I feel like that's super weird. Model dot. All right, well, I'm gonna just import this whole thing. All right, sorry guys. Stat model, import OLS. That should be fine. Wow, I don't know what's going on with my computer right now. Just give me a sec. Apologies for this. I'm just checking to make sure that I have everything right. There we go. We're just going to import this. Thanks, Matt. It was the dot formula. Let's see if that works. Go. Ha, all good. All right, so given that you have all the right things imported, you should get this output. In terms of the things to look out for here, exactly the same as with simple linear regression. Just as a super quick recap, we're looking at our R squared and adjusted R squared if you have a lot of variables. We're looking at our p-values. We don't want any p-values above 0.05. And then when we interpret, we are also going to be interpreting our coefficients. Any questions so far? All right, so the way that we interpret this, exactly the same. The way you interpret R squared is instead of one variable explaining the variance in your miles per gallon, all of these independent variables explain about 82% of the variance in miles per gallon. And again, looking at these p-values, something like this for cylinders, you would say that you fail to reject the null hypothesis that the coefficient for cylinders is not 0. So basically you're saying that with this high p-value, the coefficient for cylinders is very likely to be 0. Anything else that I'm forgetting to mention here? I don't think so. And I guess really quickly, the way that you interpret something like this, for all of these variables, it works the same way. So a 1 unit increase in acceleration is going to bring you a 0.159 increase in your miles per gallon. And it's the same interpretation for all your other coefficients. All right, so this is how we run a multiple regression. Next, we're going to talk about categorical variables. So categorical variables, just to do it really quick, let's take a look at some EDA. So with this EDA done, just looking at scatter plots, and here they're basically plotting every variable with miles per gallon, which is what we're trying to predict. And just based on that, based on the way that the scatter plots come out, maybe you might consider creating some categorical variables. Usually, ones that you want to consider categorical variables for are ones that kind of look like this, when you have all the points, bunched up along a line, because that means that, in terms of origin, they're basically only 1, 2, or 3, and you might want to consider them to be categorical. So to do that, there is a very, very convenient get dummies function. And all you have to do is feed it in the column and it'll create those dummy variables. And then all you have to do is concatenate, because each of these get dummies functions returns a new data frame with a column for each category. And then you just have to concat them together. One thing to note, or two things to note, this prefix of cylinders, if we actually take a look what it means, let's actually take a look at cylinder dummies. Having the prefix of cylinders basically allows you to, this 4, 5, 6, and 8 were the values in cylinder. And then having that prefix just tells you, it's just how you make the column name so that you can still identify where it came from. And then this drop first equals to true actually prevents multicollinearity. And we'll talk about multicollinearity in a little bit right after this section. But basically, if we were to keep every single dummy column, what they're saying is you can deduce one column with a combination of 4 other columns. So in this case, we had a cylinder 3 that we dropped, but with these 4 columns, we can already deduce what the values of cylinder 3 are. So that's just saying having that cylinder 3 column is going to create data redundancy. So what I mean by that is, all right, if I see a 1 in any of these columns for any row, if a 1 already exists, we know that cylinder 3 is going to be 0. Contrary to that, if we have all zeros across these 4 columns, we can deduce that cylinder 3 is going to have a 1. as its value in the row. So that's what we're saying by, we can predict, we know what cylinder 3 is going to be, even though we only have these four columns. So that just prevents data redundancy and multicollinearity. That's why we always drop first. Technically, it doesn't matter which one we drop, but typically you just drop the first one. Questions about this?
Doesn't it now make that coefficient like relative to what cylinder 3 value was? I was not sure I understand that.
Yeah. So what happens to cylinder 3? Like if everything is 0, how do you capture the information of cylinder 3? So cylinder 3, I think mathematically, if you were to look at it, cylinder 3 would be captured in the intercept term. So the intercept term would include information about cylinder 3, because if you imagine, like in your linear function or in your equation when you write everything all out, if 4, 5, 6, and 8 are all 0, that implies that cylinder 3 is the case, and that information is captured in the intercept. I don't know if that answers the question exactly.
It's a pretty good answer.
Okay. All right. Yeah. There is, I'm not sure if there's a good reading. I remember reading something that made me understand. I'll look it up and see if I can find any good material that like deduces that, or that proves that mathematically. But I don't know the equations off the top of my head, but the information for cylinder 3 is embedded in the intercept term.
If you wanted the coefficient specifically for cylinder 3, would you just change which one you were dropping so you could see it?
Ooh, that's a good question. I'm not 100% sure if that is exactly how you would get the coefficient. Let's see. To get a coefficient for cylinder 3, I'll have to think about that and let you know. I'll make a note about that to look at how to get coefficient for the dropped variable. That's a good question. I'm not 100% sure, or I don't remember right now, but I'll look something up and have an answer for you on Slack. But yeah, that's something I'll look into. One other question I wanted to pose. If you were to take a look at something like year in this code, and this code I adapted from some of your lessons, in this example, they decided to turn year into a dummy variable. Does anyone have any thoughts about that? Like, why turn year into a dummy variable? Because year is still kind of continuous. Any thoughts? Does anyone see that and be like, why would they want to create like a single column for every single year? Okay, that's fine. Well, whether you keep something like year, and in our project that we're going to be doing, a very similar variable or a couple similar variables that you'll have to this is, in our project, we'll be predicting housing prices, and some of the variables that are provided include like number of bedrooms, number of bathrooms. And so some people like to keep them continuous, and some people like to turn them into categoricals. Now, when would you do which? Typically, if you believe that there is a linear relationship between year and miles per gallon, let's just take a look at this example. Let's just say that, all right, you can still kind of see like this upward sloping pattern across all the years. So basically newer cars have higher miles per gallon. If you're going to make that assumption, then you can keep it as continuous. However, let's say you have a slightly different pattern, and you can sort of see here with the density of these points, it's a little hard to discern. But let's just say that, for example, if our overall pattern, if let's say we plotted the mean for each one, and let's say instead of sloping up, maybe there's just like one year in particular that like maybe, I don't know, 76 has just like a really unusually high miles per gallon, then you can take a look at turning them into categoricals, just because you are not confirming that, with every year, miles per gallon gets faster or higher. Faster? Higher. If you believe that there is that linear relationship, though, you can keep it as continuous or turn it into or if you don't, turn it into categorical. I will say there is no correct answer. For I think a lot of the projects, people just try both and see which one makes more sense or which one has lower p-values. Couple downsides: when you turn things into categorical variables, you end up with way more columns. So you have a lot more data to look at, which is sometimes a good thing, sometimes a bad thing, can be very overwhelming. But we'll talk about feature selection really quickly at the end as well. But questions about that? I don't know if anyone has any questions about what I mean by, like, can we keep something that looks categorical continuous? All right, so I also wanted to talk about how you interpret a categorical variable's output. So let's run this. I think I've already run this. And here you can see, instead of typing out all the columns, I use this really neat join statement. Now with this summary, you can see that it's a little bit longer, but now each coefficient we would interpret slightly differently. So as you can see here, let's use cylinders as an example. So the data that was in cylinder 4 is either a 0 or 1, whether it's 4 cylinders or not 4 cylinders. So what that means is relative to, so let's say you have 2 cars, one with 4 cylinders and one with 5 cylinders. How would we interpret this, and how would we weave these coefficients into the interpretation of that? Basically, if you have a car that has 4 cylinders, it'll take whatever relative price plus 69399. And then whatever, if you have a car with 5 cylinders, you would add 6.6377. So on average, cars with 5 cylinders is about 0.3 miles per gallon lower. So it's kind of a relative thing when you're doing coefficient analysis of dummy variables. Actually, this is where you can sort of take into account comparing with the 3-cylinder option. There is no explicit 3-cylinder variable here, but you can also say, all right, 4 cylinders compared to 3 cylinders, 4 cylinders is 6.94 miles per gallon higher than 3 cylinders. So you can think of 3-cylinder as a zero value, because relative to that, the other cylinder values will be that much more than the 3-cylinder values. I don't know if that was English or if that was coherent. Does anyone need me to repeat that?
Yeah, can you explain it one more time?
Okay, yeah. So, so comparing these coefficients to each other is just doing like a relative comparison, right? Everything else held constant, a car with 4 cylinders would be 0.3 higher miles per gallon than 5 cylinders, just because the difference in these coefficients is about 0.3. So that's comparing dummy variables in the same group to each other. Now, this is where we can also talk about the one that we had dropped. So the one that we had dropped, anything that has 3 cylinders has zeros for all of these values. So you can sort of imagine if, because of the way our linear regression is set up and the linear regression formula is set up, and that being, let me see if I can like draw it out super quickly. So our linear regression formula starts with like y hat equals to, it's going to be coefficient multiplied by variable value, variable. And it's going to be this for every, is that how I spell it? No, yeah, CLE, there we go. So it's going to be coefficient times variable plus coefficient times variable plus coefficient times variable for all of these variables. So imagine if something has 3 cylinders, we have coefficient times variable for each of these, right? Each of these 4 will have some part of this equation. But if something is 3 cylinders, for 4, 5, 6, and 8 cylinders, this actually goes down to 0 because the variable amount will be 0. Does that make sense? So because of that, each of these cylinder values relative to a car with 3 cylinders will have this difference. Did that help?
Yeah, that makes more sense.
All right, yeah. Another way to sort of think about it, if let's just isolate it to 3 and 4. Actually, let's isolate it to 4 and 5 cylinders for now. So here we have our 4-cylinder value, and it's either going to be times 1 or 0. whether it is a 4-cylinder value or not, we have our 5-cylinder value, which is 6.6 times 1 or 0, depending on whether it is or not. And this is all part of our equation, right? We're considering this variable with all our other variables, and y hat is our prediction. So if a car is 4 cylinders, this value is going to be 1, this value is going to be 0. So everything held constant, the car value will go up by 6.9. So this is the case if your car has 4 cylinders. If your car has 3 cylinders, this value will be 0. Let me draw that real quick. This value will be 0. This value will also be 0. All of the other cylinder values will also be 0. So therefore, you can say if we're comparing a 4-cylinder to a 3-cylinder, there is going to be that 6.9 difference. There's going to be that difference there. Cool. All right, let's move on from that. This requires a little bit of thinking, but I will send out a couple readings for this that will hopefully help as well. All right, so let's see, where was I? So all of these categorical variables, you'll interpret them in different ways. So one thing that will tell you whether it made sense to turn something into categorical or not is, for example, for a year, you expect that if something is newer, it will have a higher mile per gallon value. And you can sort of see here with each of these years increasing, the coefficient overall kind of does increase. So you can see like something being a year 71 has a 0.91 coefficient. So it adds 0.91 to the miles per gallon value. 72, 73, it does go negative a little bit. But overall, there's kind of an upward trend as we get to newer and newer years. Until we get to like 80, we have like a +9 for miles per gallon for a car that's made in 1980. And so you can sort of see that, all right, if it's not constantly going up, maybe turning it into categorical variables does make sense. Questions about that? All right, well, again, very, very important to always interpret your coefficients in context. I know I don't know anything about cars, so I could be explaining this all wrong. But when dealing with housing prices, just take a look at your variables. For example, if you see like, I don't know if this makes sense, but let's say you expect that a car with faster acceleration should have higher miles per gallon, then you want to see a positive coefficient. This case, I think it also makes sense because if you have a lighter car, you have lower miles per gallon if you have a lighter car. So I think that makes sense as well. But always, again, interpret your coefficients with context. All right, questions about categorical variables? All right.
Sorry, I think maybe somebody asked this already. I'm jumping in like a little bit late, but
no worries.
For certain categorical variables, I don't understand why some of them have like, I guess, p-values that would be above our threshold while others wouldn't, and like why it would make sense to take out those specific categorical variables versus taking out like the whole category.
Oh, okay. So just to clarify, you mean like, for example, with like all these years, some of them have high p-values and some don't.
Right, like some years don't seem to be like as correlated, I guess, as other years, which I don't understand.
Yeah. So what happens when you turn something into categorical variables? You're basically turning what used to be just a one-dimension feature. So year used to be just like one dimension, just all your years in one dimension. What you're actually doing here is you're creating a new dimension for each different category. So the effect of that is you get to you're actually here analyzing it in more of a perspective of, was a car made in 1971? Was it not? So because it's using that, is more asking that question, whether a car is made in 1971 or it's not. Something like, for example, a car being made in the year 77, or actually being in all these years, 77 through 82, that the effect of those years is significant, but these high p-values for example, like 75, what that's saying is it doesn't matter if a car was made in 1975 or not. It just matters if, you know, there are these other specific years that are significant, but some years are just not significant. Does that make sense?
Yeah, that makes a little bit more sense. So then the idea would be to drop the years that just are not as significant.
Yeah, that's right. So in this case, like it looks like you would want to drop everything from 71 through 76, just because those years have less significance on.
So they're not going to have any real like correlation with miles per gallon, whereas other
that's right.
years might.
That's right. Yeah. So basically, it's just saying like there might be some relation there, but it ultimately doesn't matter. There is no significant effect of these years being part of the car, or these years being the year that the car was made on miles per gallon.
Okay, got it. Thank you.
Yeah, you're welcome. Anything else regarding categorical variables? All right. One other thing to talk about with categorical variables that I don't have in this notebook, unfortunately, but you can also consider turning some of your continuous features into categorical variables. Like, for example, I don't know if there's a good example here, but yeah, let's just use this for example. Here in displacement, let's just say you want to see the effect of turning this into a categorical variable. And when you would do that is if you suspect that there is a different pattern within different bins of displacement. So what I mean by that is, let me just draw this to like, imagine that we can divide our displacement into, that is not a straight line. So there we go. Imagine that we have binned it into like hundreds. And let's just say that, all right, I think I have like a relationship here that looks like this, a relationship here that looks like this, and a relationship here that looks like this. And if you remember, one of our assumptions for linear regression is a linear relationship between each independent variable with your dependent variable. One of the things that you can do to get around that is by binning your variables. So it can be, instead of doing displacement as like these specific values, you can turn these into their own categorical variables, maybe calling this like displacement 1, displacement 2, displacement 3. Of course, you have to remember what those 1, 2, and 3 mean. And then just testing your model and see if this works maybe more or less effectively than keeping it as is. These are, of course, things to do like, you know, after you've done all of the basic things and you want to see like, all right, I feel like I could still improve this a little more. What else can I do? That's something to consider for sure. All right, so with that, let's move on to multicollinearity. So multicollinearity basically talks about collinearity or correlation within your independent variables. This was something that we didn't talk about with simple linear regression because simple linear regression only had one independent variable, but when you're introducing multiple independent variables, you have to talk about or think about multicollinearity. And it's actually, that is one of the added or additional assumptions of multiple linear regression. And so what that, the implications of that, basically, if you have two independent variables that are correlated with each other, it does lead to some model redundancy. So for example, one really easy thing that you can do to check for this is, I like to do data.core because I do like to see my numbers. But you can also do like a scatter plot, or I think some people like to do heat maps as well, just to look at, and you'll have like extreme colors based on if something is very correlated or not. But I personally like to use the numbers because I think it's a little bit clearer. So as an example, let's look for something that has a high correlation. Of course, this data.core is a pandas function and just takes every column, plotting it against itself. So let's see, two very highly correlated independent variables are displacement and weight. And you can see here that they have a 0.93 correlation with each other. So if we were to include both displacement and weight in our multiple linear regression model, you have some sort of relationship between, for example, displacement and miles per gallon. So you can sort of see we have this sort of relationship between displacement and miles per gallon. But because weight is also highly correlated to displacement, that relationship between weight and miles per gallon, a lot of it is already accounted for when we're looking at the relationship between displacement and miles per gallon. So basically, we are already considering the weight effect on miles per gallon when we talk about displacement on miles per gallon, just because they are very highly correlated. They have very, very similar patterns. Does that make sense? And that just leads to model redundancy. So typically what happens is if you have, let's say, 5 variables that are all very correlated with each other, you should only keep 1 out of 5. And which 1 out of 5 you keep, it's really up to you. You can, many different ways to test. Maybe just like one way to do it is to see which one has the highest correlation with your dependent variable. Another way, literally just like run 5 different models to see which one runs the best. Or maybe comparing, throw them all in, see if one of them has like higher p-values. So many different ways to choose which of the collinear features you want to keep.
Is that why you can have like a proxy variable? Because if you know, I think this was like kind of what we were talking about before, like if you know that experience is positively correlated with like age, then you just have to have the age because you already like know the relationship between the other two, and then you can just use that one.
Yeah, exactly. That is a direct application of, or a direct, I guess, explanation of multicollinearity, because in this case, I mean, it's not exactly like a correlation implies causation, but yeah, it's saying that, you know, some of like the relationship in some of the weight is accounted for in displacement. I don't know, in a car setting that makes sense, but yeah, that's sort of saying that like displacement in some way already accounts for the patterns in weight. So we don't need both when we're.
So based on the relationship that miles per gallon has with displacement, you can infer the relationship with weight, or the other one.
That's right.
Okay.
Any other questions regarding that? Cool. So in terms of threshold, there is no real like threshold for what is too correlated. That is really up to you to test, because sometimes within all your variables, you do end up having a lot of things correlated to each other. Of course, the less correlation you have, the better. But just to see if I were to, actually, this is different. This is actually, first, let's take a look at linearity between target and features. This goes back to the assumption that your features should be linearly related to your target. And I mean, this is using correlation, which doesn't always mean that you have a linear relationship, but there's some relationship there. That's just a line of code to show that. And this is just looking at, this is just looking at the features that have, that are highly correlated with miles per gallon. Then just to subset that, I think here what we're doing is, let me just see what this is real quick. There we go. And here's just the correlation between that subset of variables. And you can see here we have a lot of pretty high correlation here. What we want to do is just drop one of the ones, drop some of the ones that have high correlation. So for example, here we're going to drop weight, cylinder 4, we're going to drop displacement, we're going to drop cylinder 8, and just basically inspect our correlation coefficients here. So really quickly, after dropping all of that, you can see that the highest correlation we have left is I think 0.77 is going to be the highest that we have left. And we'll just take a look and see how that fits in our model. In a more comprehensive modeling process, you would maybe want to run a model between each step. Up to you. So let's just quickly do that and take a look at what our model looks like. So here we have reduced all our variables to just these variables without multicollinearity. You can see straight away we have pretty low p-values. One thing to look out for if you do have high p-values is maybe take a look and see what the variable with the high p-value, if it is correlated with any other value in your feature set. Questions?
When you were looking at the correlation table, you were looking at the values as to how the independent variable, how they correlated to MPG, right? So you weren't looking at how they correlate to each other when you determined which ones you were going to drop?
So both. both. So first, because there are two things we're kind of balancing here. One, we want a fairly high correlation between miles per gallon and everything else. That we want a fairly high correlation. But on the other hand, independent variables among themselves, we don't want high correlation. So a little bit confusing, yeah. So these values on the first row and the first column, ideally we want them to be higher. And then anything within this box here, we're looking for lower. And of course, that's excluding the diagonals, because diagonal would be value with itself. So the dropping I was doing, each cell I was dropping a couple of variables. That was really just looking at, all right, where do I have high correlation coefficients within features with each other? So here I saw like weight and displacement had a high correlation, so let's drop that. I think cylinder 4 had like a 0.82 here, negative 0.8 there. So drop that. And I think same thought process going on.
But the first thing you did up above that was took
Yeah.
a sub only ones that were highly correlated with MPG.
Yep, that's right. That's just to like make it easier to do this step, to be honest. But yeah, for the linearity assumption, of course, there's a better way to do this. I think most people like to do this with a scatter plot of miles per gallon with everything else, because you can have a correlation coefficient without having exact linearity. But yeah, this is just like a quick way to do the linearity assumption test. Yeah, so we're looking at two different things at once here with correlation. We want higher correlation between miles per gallon and everything else, and lower correlation between everything else with everything else. All right, any other questions on multicollinearity? So if you have high p-values, one thing to check for would be multicollinearity, because sometimes that happens, especially when you have a lot of different variables. And why we don't want multicollinearity is because it leads to redundancy in your model. All right, I did have a quick note to talk about outliers, and I made a note to talk about it in terms of transforming features. So with outliers, there isn't like a rule of what you should do with outliers, but having outliers makes it harder for your model to predict. So for example, in your project, you might be dealing with a huge range of houses from like, I think the price estimates were literally like from like 70,000 to in the millions. And creating a model that, you know, predicts from 70,000 to the millions, if you're creating a linear regression model for that range of prices, you're basically saying that all the variables across that price range have a linear relationship throughout that entire range. So that you're saying that your model is going to be able to predict for all houses from 70K to like a couple $1 million. And if you sort of think about it, that's probably not the case. You probably want to have a different model for lower priced houses versus like giant mansions. They probably have different features that are more important. So because of that, this kind of talks about outliers. When you have noisy data, you want to get rid of outliers because you don't really want your model to learn from these outliers. So typically, you're actually looking at outliers across every dimension. First, you're going to look at outliers in terms of price, which is in your project, you're going to be predicting housing price. Looking at outliers in your housing price and maybe like culling those outliers kind of reduces the domain of which you're predicting over. So let's say, I think what some of the strategies that some past students have used include just like, you know, looking at the majority of houses or maybe just the houses in the interquartile range. That will just make sure that, you know, there's a tighter boundary of what you can predict. But also not just on the dependent variable side, on the independent variable side, if you just happen to have really noisy data, your model is just going to have a tough time figuring out the overall patterns. And that's kind of the motivation behind culling outliers. Because typically in a model, you have a lot of different features. A very common way to cull outliers is just by like taking everything that's outside of 3 standard deviations away from the mean. So that's something that you can use as well. I will say that in practice, if you are tasked with building a linear regression model for your company in the future, you're going to want to look at each feature individually and make decisions based on each feature in context. But I will say for this 2-week project, or for this 1 week, technically 1 week project, we can take a more general approach to outliers. I don't know if that is helpful, but basically outliers create extra noise in your data that can hinder your model from learning patterns that you want it to learn, which is why better to call outliers. I will say for your project, the data set does have about 20,000 rows. So after clearing outliers, you still should have like a good number of data points to work with. Questions about that?
So is the standard the 3 standard deviation from the mean, or can we arbitrarily set our own basic, like based on exploring the data, can we set our own kind of cutoffs on either end? Is that fair to just kind of make assumptions in that regard?
Absolutely. I will say that for this project, and I'll talk about this on Thursday when I do the project introduction, you get to make your own decisions on how you want to clean your data. And I will say, like, I do think that getting rid of outliers is part of the data cleaning process. You can use, I think the standard is, I want to say like something about the interquartile range. I think it is like 1.5 times the interquartile range from the mean, I think. Not exactly remembering, but there are different formulas that define outliers differently. And it's really up to you if you want to use one of those formulas, or maybe just in inspecting your data set, you want to remove just like specific rows that are outliers. Or perhaps you see like an overall like linear trend, but then at the very end, the trend kind of like changes. Maybe you want to cut off all of those points. So it's up to you to make those decisions. All you have to do is, if you're doing something, if you're doing anything in your data cleaning process, just document why you've decided to do that. If your reason is, we're just going to use a general formula for all outliers, you can just say, well, maybe I'm doing this because there are a lot of variables here, and this is just going to be a quick way to do it. That's also a valid reason. But something that I will say for this project, I want to see more documentation of your processes. So overall answer to Adina's question is, doesn't matter how you get rid of outliers, just say a little bit on what you're doing and why. All right, anything else on outliers? Okay, so transforming features is a little bit of a tough one to talk about now, and I'll go into why. For the lesson that talks about transformations, they basically list out all of these different transformations, and there are different cases to use each one. And you can see here that I will say the main one that you're probably going to use for this project is log transformation compared to the others. So just a quick overview. In the transforming features section in your lesson, they talk about log transforms, which basically you are going to take the log of every value. And I'll go into more detail in a little bit. And then you have all these other different kinds of things. You have scaling, and you have standardization, which is literally just taking the z-score. So that might look kind of familiar, minusing the mean, dividing by standard deviation. That is also a different form of scaling. There is normalization, and there's vector transformation. So two groups of transformations here. First, there is the scaling. And I want to say that scaling for this project might be a little bit less useful. We'll be talking about models next phase that require scaling, and I'll get into that when we get there. But scaling, if you think about scaling, it doesn't actually change the distribution of your data. So if you had let's say your data, your histogram looks something like this, and maybe this range is 0 to like, I don't know, 70,000. So for example, if you had that, if you used any of these scalars, like if you did min-max scaling, min-max scaling will basically turn this into 0 from 0 to, instead of 70K, 0 to 1. But the distribution of your data will be the same. It doesn't change the way that, you know, this feature is related to your target feature, because the shape of your distribution is the same. The coefficient will be different, but p-value will be the same. Similarly, if you were to do standardization or mean normalization, these have the same effect, maybe not 0 and 1, but the shape of your distribution will not change. So that's why I am it will be less likely that you will be using these transformations. So in comparison to these transformations that don't have any effect on the distribution, doing a log transformation does. And I think I have examples here showing that. So doing a log transform does change the distribution of your data. So let me actually quickly show this here. Previously, you have, I think a good one to look at would be horsepower and weight. And you can see that these are kind of skewed. They're heavy on the lower ends. By doing a log transform, and for those of you who are curious, a log graph kind of looks like this. So this is X, and if you log anything, it looks like that. This is what the log graph looks like. This is not super important, but good background info to know. If you were to log any variable, it kind of fixes the skew. So you can see for horsepower, it goes from this skewed to looking like this, so much less skewed. And for weight, same kind of, same thing here. So difference between log transform and all those other transformations, the log actually changes your distribution. So you're more likely to see an effect in how your feature can play into your model. Questions about that so far? So for this project, probably you might do some log transformations. Like before you do any of the min-max scaling standardization, you would probably do log transform first because that one actually changes the distribution of your data. Now, there is one scenario in which I can see for this project you would want to use any of these scaling, is that when you're log transforming, unfortunately, you cannot take the log of a negative number. That's just how the log graph works. You can see here, it actually doesn't cut the 0 here. If you were to look at a log graph, this kind of like approaches the 0 line, but never actually touches it. It's like, it's an asymptote, if everyone knows what that means. So you cannot log a negative number. So that would be a reason to first scale your data. So let's say you have a variable like, let's see if there's any examples here. Let's just say that you have, I don't know. Okay, I know that one of the variables in your data set are latitude and longitude. Maybe you want to transform that. I don't know. Maybe you want to log transform that to see what that does. But in your data set, those values are actually negative just because of coordinates. And so because of that, if you try and log transform those variables, you run into infinity errors. So because of that, you first want to scale it such that the values are positive. So you can choose to either, I think min-max scaling between 0 and 1. Yeah, you can choose a min-max scale. All your values will be positive. Then you can log transform. So that's when for this project, I think is a more, it makes more sense to do scaling in those scenarios, just because these scaling don't change the distribution of your data. Questions so far? I feel like that was a lot of words. Okay, so next I'm going to talk about each of these other scalings and when you might want to consider using which. So one thing I wanted to talk about with scaling is some scales are bounded and some are unbounded. What I mean by that is, for example, min-max scaling here, you can see that all your values will end up being 0 and 1. Basically, whatever your minimum will be scaled to 0, whatever your maximum was will be scaled to 1, and all your values will be in between that. Sort of just like shrinks your feature set into between 0 and 1. Similar to mean normalization between -1 and 1. Some of them are unbounded. So for example, standardization, by using this formula, your values will still not be bounded. You can have very, very large z-scores, very, very small z-scores, but it just like sort of recenters your data. So in that case, it'll be unbounded. So something to think about when you're deciding what kind of scaling to use. Does your model require a specific range of values? So sometimes models work better when you have like all positive, or like maybe it can take negative values, but you just want things on the same scale. But think about outliers. If you have a lot of outliers in a feature, doing something that is bounded might affect that negatively. So imagine if we have a distribution that looks like, okay, that's not a straight line. Let's undo that. So let's say you have, let's say something that looks like this, and then a bunch of outliers there. Typically, before we call outliers, you would think that, all right, the main part that I want to look at is probably just between here and here. So best scaling would have this at 0, this at 1. But because of that outlier over there, instead of that end part being 1, 1 actually gets pushed all the way out there. So because of that, you'll sort of end up seeing, I guess in this example, most of your values being between 0 and like 0.3, for example. So it just leads to a weird distribution of your data between 0 and 1. So that's one thing to be careful about, scaling features with bounded scales when you have outliers. We will talk about scaling a little bit more in depth at the start of the next phase, because there will be some models that work much better when you scale your data. So we'll get more into that later. But just to recap for this phase project, most likely you'll be doing log transforms to change the distribution of your data to see if that helps your model or not. And also possibly doing like a min-max scaling just to get all your values positive so that you can successfully log transform. Questions about that? All right, and really quickly, just wanted to mention the unit vector transformation. I know it looks a little bit weird, but what the unit vector transformation is, you can actually take a bunch of different variables here and combine them or coerce them into one single variable. So that's what a unit vector transformation is. So for example, you can take like acceleration, displacement, weight, and then just have them represented as a single number. That one is actually not used very often, but good one to know what it means. All right, questions so far? Cool. So here you can see we've done some log transforming here to just change the distribution of data. So even though it isn't an assumption that your data is normally distributed, typically if your data is normally distributed, it does tend to perform better in your model. Okay, so in this example here, they've done a bunch of different transformations. So they did a min-max here, right, min-max over here. This was I want to say this is the standardization because you're minusing the mean and doing it over standard deviation. This I think is mean normalization. There we go. Mean normalization there. And then this one is, again, I want to say min-max. All right. And as you can see here, these, even though they have been scaled, all that changes is the values of which they are bounded by. So now acceleration is between 0 and 1, but the distribution of acceleration is exactly the same. Just the numbers are different. So that's what scaling does. It doesn't change the shape of your distribution, just changes the values of which your distribution is bounded by. And similarly, you can see here we had, this is pre-scaling. So pre-scaling, we have, let's see, horsepower looking like this, between 4 and 5.5. After the fact, horsepower kind of looks still the same. Actually, it looks exactly the same, but instead your values are between 0.5, negative and positive 0.5. All right, so that is scaling.
How do you interpret those? Like, does that make it harder to interpret then when you're looking at coefficients?
Yes, absolutely. So that is something that I have to talk about. So when you have scaled variables, and let me just quickly see if I have an example here. So let me run this model, and this model I believe has the scaled variables. Let me run this really quick. This we haven't really seen yet. Let me see. All right, let me run this model with this data. I'm surprised that I don't have the code to run it here. Let me do this super quick and talk about the coefficients. So let's do that here. Formula here, and this is going to be data. Now let's move it down here. This is going to be data bin, and then we're going to run this model. All right, so formula data is going to be, might run into errors. Oh, nice, no errors. All right, so the ones that were scaled were acceleration, displacement, horse, and weight. Acceleration was the one that we only log transformed. So one thing I actually want to recommend is when you do a transformation, keep it in the variable name, just so that when you see it in this table, you won't forget. But this acceleration isn't just acceleration, but it's the log of acceleration. So what that means is a 1 unit increase in the log of acceleration decreases miles per gallon by 4 or 0.399. So you would interpret it in exactly the same way, just that instead of a 1 unit increase in acceleration, you're looking at a 1 unit increase in the log of acceleration. So a 1 unit increase in the log of acceleration would be equivalent to a 1 unit increase in the exponent of 1 of log. So actually, let me actually type this out super quick. If I have 1 unit increase in log of acceleration, this leads to, there we go, leads to a, let's just say -4 of miles per gallon. So when we have that, you can reverse it. So 1 unit in log acceleration, what is that equivalent to in just acceleration terms? I think you just do the exponent of 1. And I think that's what gives you miles per gallon of -4. I do have linked in your project guidelines the exact interpretation of that. So this is your project guidelines, which is already linked in the homeroom for anyone who's interested. I do have a resource here because I always forget which way I have to unlog it. But here I have, if you have a log of a variable and you didn't log that. So for example, here you have beta 1 being the one with the log x. This is the interpretation. If we increase x by 1%, y will increase by however many units of y. So yeah, that's the interpretation of that. If you have scaled it and logged it, that gets even more complicated. So you first have to unlog it and then unscale it. So it does depend on the order of which you are doing your transformations. You do have to remember them and reverse them accordingly. Questions about that so far? Yeah, that's something I can't believe I forgot to mention. Let's see. One final thing to mention. Actually, no, I'll talk about that later when we get to our train test split. So we're closing the chapter on transformation, but I am going to talk about it in a little bit after we get into this train test split. So train test split is not in topic 18. It's actually talked about in topic 19, but I did talk about it last study group. So we have hopefully tried our train test split with simple linear regression at least. And those of you who are working on mini projects, hopefully you incorporate train test split as well. But what do we do train test split for? Because we are creating predictive models, we want to be able to see how well our model is at predicting unseen data. And so typically what you'll do is you'll take a smaller proportion of your data set and hold it aside and do your model training on only the train set. And typically it's an 80-20 split. So you'll train your model on only 80% of the data, not considering anything about your 20% of the data. And then after that's all trained, you can actually take your 20%, run it through the model and see if the predictions are accurate. And we'll walk through exactly how to do that here. With train test split, we're going to introduce a new library. We did talk about this last time, but Scikit-Learn is the library that has our train test split method. Let me actually quickly run this. So with your train test split, we're using Scikit-Learn. There are 2 different ways to do it. If you already have your X's and Y's split up like this, you will do it with X train, X test, Y train, Y test. But if you just have your data, and actually let me just run this first, and then let's take a look at X train. You can see here that this is some of the rows, and they've shuffled it because it's a random split. 317 rows here. X test has 80 rows, so it's about, yeah, about an 80-20 split. Again, random rows. Y train, Y test, the same, but these are just your miles per gallon values. Different syntax of doing this is if you don't have your X and Y split up yet, you can actually feed it in a data frame and give it train and test. I believe that will work. So if you want to do it this way, it's also acceptable, exactly the same results. You'll have your train being everything here. You still have your miles per gallon with your features, and then tests will be the same, but just smaller. So just wanted to let everyone know that syntax. So depending on which library you're using, you might want to do it differently. Why I say that is because there is another library that has a linear regression model that is actually easier for testing. So within Scikit-Learn, you also can train a linear regression model. So some pros and cons with your stats models. So there's stats models in their Scikit-Learn. With stats models, you have this really nice output you can use to take a look at your p-values, and everything's just much more visual and easier to see. With Scikit-Learn, you don't have that those visual cues. So usually, one would train their model using the stats models regression, and then when you're done with that, you use the Scikit-Learn one just for your final model, or maybe a couple intermediate models for this step. This step is important because you can see how well your model is doing at predicting on your testing set. And I think I talked about this example last study group when we were doing like the weight and height one, but just to do it again with this library this time. The syntax for doing a linear regression in Scikit-Learn, and actually any model in Scikit-Learn, and as a preview, our next phase is all going to be models out of Scikit-Learn. This is the way you do it. You first start by instantiating the model, basically saying, all right, I want to fit a linear regression model. And then in the second step, you fit your training data. So the reason why you have two different ways to do the train test split is, as you can see here, Scikit-Learn takes in your feature set with your dependent variable separately. That honestly, you can also do it this way and then split them up after the fact, but the same thing. So what you do first is you fit your data to your train set, and then you can get your different prediction values. So here you can see here with Y hat train, these will be all my prediction values for things in my train set. Here I can also predict on my test set. Some things that you have to make sure are right when you're doing feature selection. So maybe you drop some features in your train set, you have to make sure to drop the same features in your test set as well. So once you run that, you can see that in Y hat train and Y hat test, each of them is an array of predictions. So these are your predictions for Y hat train. These are your predictions for Y hat test. And this basically gives you a very comparable metric for how well your model is doing at predicting. So for miles per gallon, and if we run this really quick, mean squared error is the built-in function in Scikit-Learn that you can get the mean squared error. So all you have to do is feed it in the two arrays of which you want to calculate mean squared error across. So here I'm doing it for the train, and Y train is the real values of miles per gallon. Y hat train is the predicted. Same for test. You get this mean squared error. Squared only has one R, by the way. This I copied from the lessons. But then just to get something that is a little bit more comparable and to scale, because it's a squared error, I like to take the root mean squared error. So I'm just literally taking the square root of that. And basically what we're saying is in our train set, our average error was about 4 miles per gallon off. And in our test set, which remember, our model didn't take into consideration any of our data points in our test set, we have an error of about 4.6. And so this comes back to the notion of overfitting. If your model is overfit, you will see a huge difference between your training error and your testing error. Because overfitting means that it has learned your train set very, very well, but has failed to generalize to your test set. So usually that's just one of the last few things that you check, whether you have overfitting in your model, and you do that by looking at your mean squared errors or root mean squared errors. Questions about this so far before I go back into talking about the transformations?
Say that your data was overfit. Would you go back and change? I just lost my train of thought. But
yeah, basically what do you do if your model's overfit?
Yeah, would you change the training set size, or would you actually change your model itself?
If your model is overfit, typically, I mean, one thing you can do as like a sanity check to just make sure, you can maybe just try a different train test split and see if it's still overfit, because it could be that you just have like a really wacky test set that so happened to take, like, for example, all the outliers. So that's one reason for taking out outliers as well. But if your model is overfit, some things that do lead to overfitting, I think I did see in your answers to today's warm-up question. If you have a lot of features, it leads to a higher R-squared, which leads to higher chance of overfitting. So maybe you want to sacrifice some of your R-squared and use fewer features to predict. Overfitting, there are actually a whole set of methods to deal with overfitting, but we won't get into them until the very, very beginning of next phase. So apologies for that suspense. But if something is overfit, at this point, something that we can do to combat that would be just reduce the number of features that you're using to predict. If anyone wants to try out any of those techniques, I will list them. I'll actually put them in the guidelines just for people who, if you have extra time after doing this project and you want to solve for overfitting, I will link some resources that you can read into, but we will be going over them at the very start of next phase anyways. So for this and where we're at with overfitting, we know we can check for if it exists, but we haven't talked about the formal methods to get over those. Any other questions with regards to this?
What about underfitting? How can we tell if it's underfit?
Yeah, underfit, you don't really have, basically underfit is when your model has failed to learn anything about your data and you're just looking at high errors across the board. If you have, specifically for linear regression, underfitting can be directly checked for with your R-squared. If you have a low R-squared, it is underfit. But something that I will also double check is sometimes you might end up with a lower R-squared, but you would also want to double check your RMSEs. If you have very underfit a very underfit model, typically your errors will be all over the place. With different train test splits, you'll end up with very, very different error values. Something that we can talk about here, and I don't know if I have it in here, in the next study group, there's something called cross-validation, where it'll actually split your data into many different parts and then look at the error values across that. And if your errors are very, very different across all the splits of your data, you do have underfitting. But if you're underfitting your data, that just means that your model is failing to learn any of the patterns in your data. Probably you want to introduce more features or take a look at the assumptions as well. Maybe there's just like no linear relationship for your model to learn from. Any other questions about this?
And I just had a quick question on predicting too, specific numbers for a variable, because I think they mentioned that in one of the lessons, but they didn't show how to.
Yeah.
And I'm confused.
Yeah, absolutely. So how this function works, the prediction function doesn't work well in stats models for unseen data, which is one reason why we also introduced the Scikit-Learn linear model. But if we take a look at how this function works, let's see, it takes in X test. So the predict function will take anything with the same number of columns as your feature set. So for example, here you can see that what it's doing here is it's going to take each of these values, plug it into the equation that your model has fit, and then just give you like the prediction of Y. So all you really need to do to use this .predict function, let me see if I can like get it right on the first try. is if you were asked to make predictions, you would have to like make sure that you have an array that matches the same shape. So I believe you want to do, like, for example, all right, let's take acceleration to be like 0.5. I know these are scaled, so I'm going to use numbers like this. Origin 2 is 1, origin 3 is 0. They might give me, that's right. So let me just double check. Contains a single sample. We want to do this, just reshape our array. Oh, wait, I want to do it here. And this will give you your prediction. So all you have to do is just make sure that you're feeding it in an array of numbers that matches the same dimensions and also the order of your data frame that you had fed it in, that you fed into the model to fit. And once you've done that, you can just feed it in an array like this, and this will be the prediction for basically something that has a log acceleration of 0.5, a scaled log weight of 0.1, origin 2, not origin 3. Questions on that?
Thank you. That's super helpful.
Awesome. Awesome. If you have multiple, you can also do multiple arrays. You just have to reshape it a little bit differently. Okay. The last thing I wanted to talk about was something else that's related to data leakage, and it does bring us back to transforming features. So when you're transforming features, especially some of these transformations, so if you take a look at min-max scaling does depend on what subset of your data you're looking at. So after we've done a train test split, we should only do our scaling on the parameters of the train set. And that prevents data leakage. So because we're assuming that our model has no information on the test set at all, we're going to have to scale our features with parameters of the train set. So if we're scaling our variables, this min and max are going to be the min-max values of our train set specifically. May or may not be the same as your test set, but to be safe, you're going to use your parameters from your train set. And for example, let's say for this case, you have like a max of 10, a min of 0. For your test set, maybe the max is 11. You're still going to scale it with the parameters of your train set. And that's just prevention of data leakage. As another example, when you're standardizing, you see how we're using the mean and standard deviation or standard error. We're going to use the mean and standard error of your train set, not your test set. Your mean and standard error is going to be different across both sets of data, but you want to do it with the parameters of your train set because you're assuming that you only have your train set and your test set is going to be completely unseen. Questions about that? So because log transform is just taking the log of values, technically log transform doesn't matter if you do it before or after you do your train test split. Cool. I think that was the last thing I wanted to mention. Does anyone have any overall questions? Okay, so right after this, I'm going to send out the pairs for the end of phase project. Again, if someone is ghosting you or is not replying to your messages, please let me know as soon as possible, especially before I leave. So I have that. I also have the guidelines for the next project up already on the homeroom. I think I have linked it at not just the bottom of the homeroom, but I have it right at the top here as well. So if you want to start looking at it, do that. But I also will be going through each of these processes when I introduce the project on Thursday. The mini project, I would say get that done soon, the sooner the better. I will be looking over it, and rather than your exact model results, I will be looking for the procedures of your project. So just making sure that you're doing your train test split right, or your data cleaning makes sense or doesn't make sense. So I'll more be looking out for, I guess, if your code is coherent or your process is coherent, rather than the how well your model is trained. That is less of a priority for me. Let's see, any other questions? Let me see if there's anything that I wanted to talk about. Cool, yeah, for that mini project, as long as you get it back to me by, I would say, preferably before Friday so I can send any feedback if needed. But Friday is fine as well. Also, I have put up all of the information for the week that I'm out. So we'll have a bunch of these really awesome other instructors that will be covering all of our sessions. All of them will be linked here because they will be using their own Zoom links other than our usual ones. They will probably also Slack the channel, so please do say hi. I think Amber has actually left a little note for you all, just introducing herself and saying hi and what she wants to talk about during those office hours. Cool. I don't think I have anything else. Final call for questions. All right. Final reminder, tomorrow is a day off for Flatiron School, so I will not be reachable, but I'll be back to answer questions on Thursday. Again, a couple of you have one-on-one scheduled for tomorrow. If you still want a one-on-one this week, you can reschedule. If you can't find a time, let me know, because I do think my calendar might be filled up. All right, well, if there's nothing else, I wish you all a good rest of your day. Work on your mini projects. If anyone needs like a Zoom room that they rather work on rather than whatever other software you're using, let me know. I can set that up for you as well. All right, well, have a good rest of your day, everybody, and I will talk to you all at one-on-ones later today or on Thursday. All right, bye.
Thank you.